Welcome back to IO Creed. Last episode, I showed the engineering pipeline for making a robot dance mapping human motion trajectories to its joints, training a robot control neural network through large-scale simulation and reinforcement learning, then deploying it on the robot to precisely reproduce human motion. We used a simple MLP with only 250,000 weights, trained into 2 for hours on one GPU. If Embodied AI research is an interstellar voyage, then congratulations by finishing the last episode. You have completed the rocket launch stage. Next, we will pilot the spacecraft and officially begin our journey. In this video, I will introduce NVID, IA's open source S when I see framework, which truly enables robots to follow human motion trajectories in real time. From now on, your robot can become your avatar, just like in real steel. As usual, this episode is split into 2 videos, theory first, then hands-on practice. Most importantly, our open-source one-click deployment tool, IOENV, will be updated as well, helping everyone watching quickly get started with S when I see training, simulation, and deployment. I also recommend that so NIC author Zheng Yi's own talk before returning for our framework explanation. First, let's briefly see which dimensions are being scaled up by the supersizing in the SONIC paper's title. First, the base scale increases hundreds of times. The SONIC team open sourced the 288 hours of human motion trajectories used for training, containing more than 140,000 motion sequences. From basic walking and running to hardcore martial arts and dance, they cover the main motion types in work and daily life. Next comes parallel acceleration for motion retargeting. Retargeting a dataset this large on the CPU, as in the last episode, could keep the computer running for 1 or 2 days. Fortunately, C-Team also opened or the SOMA retarget tool. Its CUDA solver processes Doja in batches, cutting the process to under 2 hours. Next, the model architecture expands dramatically. SONIC upgrades the original 250,000 parameter network directly to 22.5 million parameters, increasing capacity 90-fold. Its architecture also differs substantially, which we will explain in detail shortly. Now consider the number of simulation environments. Previously, one GPU training ran only 4,096 simulations. SONIC trains on a 128 GPU server cluster, with 4,096 simulations on every GPU, making exploration 128 times more efficient. More striking is the training time. One motion previously took only 2 to 4 hours, but SONIC spent 9,000 GPUs optimizing the model weights to peak performance. Even on 128 GPUs, that requires at least 3 days. Finally, inference performance is optimized. The original 250,000 parameter model ran efficiently on the onboard CPU, but running the 22.5 million parameter model on the robot requires its IOENV chip for real-time GPU inference. That quickly covers the paper's key information. Let's start with the core architecture. The architecture on screen is called the Universal Token Module, which we will abbreviate as UTM. Remember this term, it is SONIC's neural network backbone and the most important innovation in the framework. Many of you may feel confused by such a complex network. Why is it designed this way? And how does it relate to the MLP from the last DMAP from the last episode? Relax, we'll go step by step. Look at UTM's robot encoder and control decoder. Together, they are essentially an expanded version of the earlier MLP. First, compare parameter scale. The NLP we deployed last episode had only about 250,000 parameters and could master just one roughly 30-second motion sequence. A different motion required retraining. Although UTM also consists of multiple NLPs, its deployed model has 22.5 million parameters, 90 times the previous count. That expanded capacity lets it fully absorb the massive 288-hour motion dataset. This parameter surge is not only engineering breakthrough, it also follows biological evolution. When humans learned to walk upright, the movement coordinating cerebellum also surged in capacity. Now let's compare the difference in temporal horizons. The old model's 157-dimensional observation contained only robot state feedback at the current time, t, and the target trajectory point at the next dt. In UTM, both dimensions increased n-fold. Its observation includes per spaceship states from the past 10 EDS and target trajectories for the next 10 EDS. Here is a vivid analogy. Controlling a robot is like driving at night. The old model is a driver with no GPS and only low beams. It sees just the current speed in the road 1 meter ahead, so it keeps braking hard and drenching the wheel in response to immediate conditions. making the whole ride very stiff. UTM is like switching on the high beams. It knows its current position and can anticipate upcoming obstacles and turns, so it adjusts in advance to keep the motion smooth and stable. From that comparison, it is easy to assume that the network grew simply because there was more data. In fact, the growth rates differ greatly. Dataset duration increased 27,360-fold, while network parameters increased only 90-fold. This means the raw motion data must contain much compressible redundancy. UTM introduces a variation alloto encoder, or VAE, pattern. Functionally, an encoder compresses the original trajectory into a lower dimensional feature space. It is then quantized and denoised, and a decoder reconstructs the original trajectory. The old model inferred directly from the target trajectory as an observation. By contrast, UTM passes the observed motion trajectory through a filtering funnel formed by an encoder and def SQ, first refining and compressing the data. UTM compresses a 640-dimensional motion trajectory input into a 64-dimensional token, then reconstructs the 640-dimensional motion trajectory through a motion decoder. But this raises a question: can that 64-dimensional token still be restored to the original trajectory? Let's use a very intuitive example to show that this compression and restoration process works. You have probably learned how to express a parabolic trajectory in three-dimensional space with polynomial equations, given only its initial position, initial velocity, and gravitational calculate its position and velocity at any time. In other words, every point on the parabola is equivalent to those polynomial parameters. Human motion trajectories are clearly far more complex than a parabola, but representation learning can still perform this feature extraction. We will explain it further in the training section. For now, we can understand the 64-dimensional token as motion intent, an abstract concept like one in the cerebellum. It resembles learning to run, swim, or dance, first imitating each movement step by step, then gradually understanding it, until it becomes muscle memory like walking. I no longer think about where to put my arms or how to move my legs. I simply let the cerebellum coordinate the body's muscles to carry out the intended motion. UTM's control decoder is like the robot's muscle controller. From its current and past proprioceptive states, it can quickly calculate the corresponding control commands based only on the motion intent. By now, you should understand turns observations into robot control commands, and see how it is similar to and different from the old model. Next, let us consider a more fundamental question: how does the 64-dimensional token manifest itself in the real world? The same motion intent can be expressed in countless ways. Take jumping. It can be a human skeletal motion curve, the joint angle curves of dozens of motors inside a robot, the spatial trajectories of the limb endpoints, a video or audio clip, or simply the word jump. If that multi annotation sounded a little abstract, this next example will make it instantly clear. I am sure you have seen those abstract basketball videos. Even when the screen shows only lines, mosaics, and Unicode images with no person in sight, those distinctive motion trajectories and color blocks instantly remind you of the idle trainee who practiced for 2.5 years. Though highly abstract, the images retain all his motion features. That is what motion features are. Let us return to the UTM architecture diagram. It shows 3 encoders for different modalities, each of which compresses a different form of motion trajectory into a token. In large language model terminology, these encoders are also called tokenizer S. Universal in UTM means a general-purpose motion controller that accepts many forms of input character animation trajectories driven by a gamma pod, human motion captured by a motion capture suit, human trajectories generated from text or video, or motion commands generated by a VLA. These motion trajectories have entirely different dimensions. Like words in different languages, they can mean the same thing yet look completely different. These encoders extract a 64-dimensional token from each form of motion command and align all the tokens in the same feature space. UTM also introduces a masking mechanism. By activating the mask for the corresponding encoder, the user can select a single motion command sources which control modes in real time, including gamma pod control, full body teleportation, and VLA model inference. At this point, we have fully understood SONIC's model architecture. How do we train a model like this? How do we ensure that a compressed token contains complete motion information? And how do we align multi-model encoders in one shared feature space? Keep watching, because next I will focus on SONIC's training method. In any deep learning paper, loss function design is probably the most important element besides the model architecture. SONIC has for losses PPO, token, reconstruction, and cycle, which can be divided into reinforcement learning and representation learning. Using the UTM just described, this computation graph details the modules involved in each loss. The reinforcement learning loss is PPO loss. It is basically the same as what we introduced in the previous episode, so let us briefly review it. It is like a teacher training the robot in simulation. Specifically, PPO loss contains reward terms and penalty terms. The smaller the robot's error in following the desired motion trajectory, the greater its reward. And the longer it survives in simulation, the more reward it accumulates. To keep the robot constrained by its hardware structure and motor performance in simulation, faster changes in motion commands, more joint limit violations, and more frequent collisions all result in greater penalties. Through this reward and penalty mechanism, the robot gradually learns to reproduce human motion accurately in simulation. Next, let us look at the three loss functions for representation learning: token loss, reconstruction loss, and cycle loss. These three functions answer the questions we raised earlier: how can a compressed token retain complete motion information? And how can multi-modem encoders be aligned in one shared feature space? In SONIC's training dataset, every trajectory has three modal representations: human motion captured from a person, robot motion rate allocated to the robot, and hybrid motion, which combines the robot's lower body trajectory with the human's upper body trajectory. UTM's encoders compress the multi-modem motion commands into tokens in the same 64-dimensional feature space, shown in the diagram as ZRs, EH, and ZM. Token loss bring the three tokens as close together as possible in the same latent space. Put simply, it makes them reach a consensus. The tokens then pass through the motion decoder to reconstruct the robot's motion trajectory, shown in the diagram as drive ZR, Dr. ZH, and Dr. ZM. Reconstruction loss makes the robot trajectory produced after compression and reconstruction as possible to the original robot trajectory, GR, in the dataset. In other words, reconstruction loss follows the same principle as the motion retargeting discussed in the previous episode, while SONIC uses a VI architecture to implicitly embed that retargeting process in neural network. Finally, let us examine cycle loss, literally meaning cycle consistency. It is a crucial step in keeping the motion intent from drifting. Human motion and robot motion pass through their respective encoders to produce EH and ZR. Although we know they correspond to the same action in the dataset, we cannot be sure whether the human encoder introduced special noise during compression, like an invisible watermark generated by AI. This noise may be nearly zero under token loss and reconstruction loss, yet the resulting tokens may still express different meanings. For example, squatting versus punching, and kicking a ball versus stepping may look very similar in terms of joint posture, but their centers of mass, ways of applying force, and subsequent movements are completely different. Cycle loss therefore provides a second quality check. It minimizes the noise introduced by the human encoder and ensures that, to the robot computer, robot motion reconstructed from human motion remains consistent with the robot motion in the dataset. Now that the loss functions are clear, let us discuss another mechanism that effectively improves SONIC's convergence speed on extremely large motion datasets: adaptive sampling. The 288-bar motion library contains many simple motions, such as standing still and walking forward, backward, left, or right, as well as many difficult motions, such as sprinting and making sharp turns. The loss function design cannot distinguish how difficult these motions are, so it uses the same standard to calculate rewards for both simple and difficult motions. To stop costly computing power being wasted repeatedly on simple motions, SONIC introduces a sampler. Think of it as a dynamic mistake log. It divides all motions into bins, then records each bin's previous execution failure rate during training. The higher the failure rate, the harder the motion, so the more likely that segment is sampled. But we cannot guarantee that every motion in the dataset is achievable. For example, stair climbing or stair descending motions are impossible in a flat ground simulation. The sampler therefore sets capped upper and guaranteed lower probability limits, so the robot neither fails to learn flying nor forgets running. Okay, after all that, some viewers will ask, as you said at the start, do we really need 128 GPS in 3 days of training for this model? Students and small teams simply cannot afford that. To find out, our team spent $15,000 RMB renting a server with 896GB RTX RO 6000 GPUs and trained for 2 full weeks. Our conclusion was that even budget-conscious users with limited funds can train a useful model with SONIC. Let's do some rough math. On each RO 6000, we ran 16,380 for simulation environments at once, 4 times the default number. 8 GPS trained in parallel for 250 hours, totaling to 1,000 GPU hours. Its sample count was already close to the default 9,000 GPU a run. And our training metrics converged to levels very close to those in IOENV's training guide. In other words, with a few small changes to the training strategy, even a limited budget can give your robot a powerful, general-purpose motor cerebellum. IOENV also looks after zero-budget users by open-sourcing a pre-trained model for the Unitree Gone on Hugging phase. It's spoofed, go try it. Now that we have trained an effective neural network model, the next step is to deploy it on the robot for full-body teleportation, turning it into an extension of your own body. So this final section introduces IOENV's real-time inference and control framework. It tackles the core questions what devices and interaction methods can provide the multimodal motion commands UTM accepts, and how can IOENV run smoothly on the robot's onboard system. IOENV offers a simple, intuitive solution just like in Ready Player One. Users can control a robot with full-body movements through a consumer-grade VR device, then switch to GammaPod mode at any time and move the robot as easily as playing a game. This diagram shows the state machine architecture used by IOENV's teleportation framework, but combinations on the VR controllers let you switch between operating modes. When activated, the state machine has two modes, planner mode and pose mode. Let's start with planner mode, the GammaPod control mode. IOENV's inference framework includes a game character motion generator called the Interactive Kinematic Planner. It takes control signals from the GammaPod, generates a continuous robot motion trajectory, and feeds it into UTM's robot encoder. It actually came out of Motion Bricks, another NVIA project, and was originally intended to control human characters in action games. But the IOENV team had an idea: if this motion generator can play Assassin's Creed, why not a humanoid robot? That makes me want to say NVIDIA really has not forgotten us gamers. Now let's look at pose mode, the full-body teleportation mode. Its human motion recognition comes from PICO's body tracker, yes, the same feature that lets you dance freely and strike all kinds of strange poses in VR chat. But in IOENV, your motion trajectory goes to UTM's human encoder to drive a humanoid robot in the physical world. Either control mode can be implemented by other frameworks on its own. UTM's clever design is what lets the two modes switch at any time. Remember the multi-modem encoders we mentioned earlier? Commands from both modalities are compressed into the same feature space. At runtime, we only need to switch the activation mask at the encoder's output, and the control decoder can interpret commands from either mode. That leaves one last question: how can this 22.5 million parameter model run on the roll beats? In the last episode, using ONNX CPU inference, even the 250,000 parameter model could only just run at 50 Hz. But the NVIDIA or an NX module in the Unitree Gone also has a GPU with 100 TOPS of compute. IOENV takes full advantage of this GPU. With Tensor RTC GPU inference, it converts the ONNX model into a structure better suited to GPU parallel computing. It lets a model scaled up by a factor of 90 still run steadily at 50 Hz. That covers IOENV's three-tier model architecture, training pipeline, and real-world deployment. Of course, IOENV has many engineering details you will need to explore yourself to fully understand. We spent so much time breaking down ONNV not simply because its model is larger and its data more abundant, but because it shows us what a truly general embodied model should look like. IOENV defines a universal control interface for humanoid robots. Whether motion input comes from GammaPod control, motion capture, text, video, or another VLA model, UTM can convert these different modalities into motion intent a humanoid robot can execute. Here, the robot must not only follow motion, but also understand the environment and objective its ease, and decide what to do next. As usual, to remove the obstacles you may encounter while setting up the environment, we have also updated the IOENV Docker image in our open source IOENV deployment tool. If you want to experience IOENV's training, simulation, and real-world performance firsthand, continue with part 2 of this episode. Please like, coin, and favorite, and keep following us.